Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 10, Projective Transformations of Two-Dimensional Forms. Section 98, Fundamental conic of a polarity in a plane. We have just seen that a polarity in a plane is given by the equations 1, rho u1 prime equals a11x1 plus a12x2 plus a13x3. Rho u2 prime equals a21x1 plus a22x2 plus a23x3. Rho u3 prime equals a31x1 plus a32x2 plus a33x3, where the absolute value of aij is not equal to 0. Definition: two homologous elements of a polarity in a plane are called pole and polar, the point being the pole of the line and the line being the polar of the point. If two points are so situated that one is on the polar of the other, they are said to be conjugate. The condition that two points in a plane of a polarity be conjugate is readily derived. In fact, if two points P equal to x1, x2, x3, and P prime equal x1 prime, x2 prime, x3 prime are conjugate, the condition sought is simply that the point P prime shall be on the line P prime equal u1 prime, u2 prime, u3 prime. The polar of P, i.e. u1 prime x1 prime plus u2 prime x2 prime plus u3 prime x3 prime equals 0. Substituting for u1 prime, u2 prime, u3 prime, their values in the terms of x1, x2, x3 from equations 1, we obtain the desired condition, namely equation 2, a11 x1 x1 prime plus a22 x2 x2 prime plus a33 x3 x3 prime plus a12 times the quantity x1 x2 prime plus x2 x1 prime plus a13 times the quantity x1 x3 prime plus x3 x1 prime plus a23 times the quantity a23 x3 prime plus x3 x2 prime equals 0. As was to be expected, this condition is symmetrical in the coordinates of the 2 points P and P prime. By placing x sub I prime equal to x sub I, we obtain the condition that the point P be self-conjugate, i.e., that it be on its polar. We thus obtain the result. Theorem 8. The self-conjugate points of the polarity 1 are on the conic whose equation is 3. a11x1 squared plus a22x2 squared plus a33x3 squared plus 2a12x1x2 plus 2a13x1x3 plus 2a23x2x3 equals 0, and conversely, every point of this conic is self-conjugate. This conic is called the fundamental conic of the polarity, also of its points. All of its points may be improper, but it can never degenerate, for if so, the determinant a sub ij would have to vanish. Chiefly exercise page 187. By duality we obtain Theorem 8 prime. The self-conjugate lines of a polarity 1 are lines of the conic 4. a11 u1 squared plus a22 u2 squared plus a33 u3 squared plus 2a12 u1 u2 plus 2a13 u1 u3 plus 2a23 u2 u3 equals 0, and conversely, every line of this conic is self-conjugate. Every point x of the conic 3 corresponds in the polarity 1 to the tangent to 3 at x. For if not, a point A of 3 would be polar to a line A through A, and meeting 3 also in a point B. B would then be polar to a line B through B, and hence the line A equal AB would, by the definition of a polarity, be polar to AB equals B. This would require that A correspond both to A and to B. If now we recall that the polar system of a conic constitutes a polarity, Theorem 18, Corollary, Chapter 5, in which all the points and lines of the conic, and only these, are self-conjugate, it follows from the above that every polarity is given by the polar system of its fundamental conic. This and other results following immediately from it are contained in the following theorem. Theorem 9. Every polarity is the polar system of a conic, the fundamental conic of the polarity. The self-conjugate points are the points, and the self-conjugate lines are the tangents of this conic. Every pole and polar pair are pole and polar with respect to the fundamental conic. This establishes that equation 4 represents the same conic as equation 3. The last theorem may be utilized to develop the analytic expressions for poles and polars and tangents to a conic. This we take up in the next section.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.